Hi, thanks, Deb. Thanks for organising this event as well. As Deb said, I'm Cameron Foreman, and I work as a quantum cryptographic researcher at Cambridge Quantum Computing. So when I talk about Cambridge Quantum Computing, I might abbreviate it to CQC, just so I don't have to keep saying the whole sentence. But yeah, so I'm going to talk to you today about achieving provable private randomness from untrusted devices. So some of you may have seen in the news over the past few months that Cambridge Quantum Computing have announced this randomness as a service. So this is the first quantum random number generator. And so I'm going to be talking a bit about the technical details behind this. So first provable quantum random number generator, it uses quantum computers, and we're able to get provable private and unbiased randomness. You really just don't have to trust the quantum random number generator is working correctly because it self-tests. And so this is a bit of a game changer in terms of cryptography because we're able to get secure randomness even against an all-powerful quantum adversary. So this means that we're able to keep our randomness private and unbiased, even against someone with infinite quantum computational power. So this has been implemented on a variety of different quantum computers. So we've implemented them on the machines at IBM. We've done this protocol on the machines at Honeywell and some of the quantum computers at AQT. And it all is using CQC's compiler ticket, and it takes care of the implementation. So we run the same circuits on these different quantum computers, but the compiler ticket takes care of this physical implementation. So it optimizes on the qubits and the circuit implementation, and so makes it super easy to run. So as I said, it is all fully implemented. So if you want some entropy keys or more information about this offering, please contact Mark Jackson. He's our scientific lead in the business development team. So I'm going to now talk about the relevance of randomness. So randomness is used in many different applications, from things like simulations to gambling to cryptography. And cryptography has the most stringent requirements on randomness. So this means that if we can use randomness in cryptography, we can use it for everything else. Cryptography is this field of secure communication. So it's things like encoding and decoding information. And so in cryptography, the security of these protocols is based on the quality of the randomness we use. So what does it mean to have secure randomness or a secure random number generator? And so the key features of a secure random number generator are that we need the numbers produced are unbiased. So every possibility has the same chance of occurring, and that they are private. So they're only known to the user. And we want these features not just to me or you, we want them in the most stringent setup. So we want them against some adversary with even infinite quantum resources. We also require that the device proves it's functioning properly. We don't want to have to trust it, because in the real world, this issue of trust is a big problem, because if this trust isn't justified, then the model doesn't hold anymore. So we don't have this security. So we need to eliminate this element of trust in the device. So we've talked about what key features we need for a secure RNG, but how can we actually evidence these features? So I'll give you a few seconds to just look at this cartoon. So as you can see from the cartoon here, we've got our random number generator in the middle, and it's producing 6 nines. And 6 nines doesn't look random, but this is the problem with randomness. We can never be sure whether this is random or not. So we must do something else. So the question becomes, what can we do? And here's a quote by one of the most notable mathematicians of the 20th century, John von Neumann. He said, "There is no such thing as a random number. There are only methods to produce random numbers." And I couldn't have said it better myself, because this means that we can't just look at the numbers and try and say they're random. We must instead look at the process being used to create them and prove that this is a random process. So this is where quantum comes in. So in quantum effects give some intrinsic random. It's probabilistic. So I've included over here the plus state, because if we measure this in the Z basis, we get a probabilistic chance that we get 0 or 1. So it's not based on any computational assumptions. This means that if we're able to use only quantum effects, we get true randomness because it's probabilistic. And I've highlighted only in bold here, because how do we know that we're only using quantum effects? And this is where trust falls in again. So I'll talk a bit about the value of trust. So here we've got a quantum random number generator. It's producing a string of bits. And the question is, how much do we trust it? How much do we trust that this quantum random number generator is only using quantum effects? And so you can kind of think of this in a scale. So when you think about trusting a device, you've got on one side full trust. So this is that we assume that everything that's happening in the device is exactly how we expect it to be. And on the other side, we've got no trust. So this is where we really don't assume anything about the device itself. It could even be built by someone trying to trick us. And so in terms of secure randomness, this area of full trust is not good enough, because quantum is notoriously noisy. So we can't build a perfect quantum process. So instead we must model to get rid of any other effects that aren't quantum. And so this is the problem, what I was talking about earlier. If this trust is unjustified, then we don't get security. So we want to try and use as little trust as possible, so no trust. And this is the goal. So when talking about quantum random number generation, standard QRNGs, they always are built in this setup where they have to rely on full trust of the model. Whereas, so the question becomes, if you want secure randomness, is it possible to do something without trust? And the answer to this is yes. And I wouldn't be giving this talk if it wasn't about using untrusted devices. So this is what we do. So we create provable private randomness from untrusted devices. So we get private and unbiased numbers using just these quantum effects. And we're also able to make the device prove that it's functioning correctly. We don't have to trust the implementation. So for the rest of the talk, I'm going to talk a bit more about what is private randomness and why it's so important. Then I'm going to talk about the approaches to random number generation and ultimately their limitations. Then I'm going to talk a bit about this new approach, device-independent randomness. After that, I'm going to talk about our specific protocol for device-independent randomness. And finally, I'm going to talk about how we actually implement this into getting the first provable QRNG with a quantum computer. So let's talk about what is private randomness and why is it important, and start with a nice example. So in cryptography, there's this protocol known as the one-time pad. And in this setup, we've got Alice in a safe space where she can prepare her message, and she wants to send a message securely to someone known as Bob. And Bob is somewhere else in a public space. So once the message or the encrypted text leaves Alice's safe space, it can be read by others. So before this protocol begins, Alice and Bob have to share some private random key. And the relevance of why this has to be private randomness is important later. So somewhere else in the universe, in this public space, we have some adversary, Eve, and Eve is trying to attack this message. Eve wants to find out some of Alice's message, or all of Alice's message ideally, but any of it breaks the security. So back to the one-time pad. So in this protocol, we kind of shuffle the message with the key. So we do bitwise addition between the key and the message in order to create an encrypted text. So we do this. So the first bit summed together equals 0, second bit summed together equal 1, and so forth until we get a full encrypted text. This is then sent into this public space. So Bob can now view this encrypted text, and so can Eve. But the good thing is, because we've shuffled this message with the key, this looks completely random to Eve. However, this is unless Eve knows any of the key, because as soon as Eve knows any bit of the key, she can work out one bit of the message. So even knowing just one bit of the key breaks the security of this protocol. So it shows why we need this private randomness. So let's formalize this a little bit and talk about what secure randomness means. So here we've got a random bit generator producing a string of bits. And again, we've got Eve's back, and Eve is trying to predict our random bits because, as I said, if Eve can find out any of the bits, they can find out any bits of the key. And we're not just talking about any Eve here, we're talking about this all-powerful quantum Eve. So Eve is allowed side information about this system. So Eve can have infinite computational power, Eve can have a full model of the RNG, and Eve can even be, like, in a quantum sense, entangled with the system. So the task for secure randomness is to get this idea of private and unbiased. So this is that the probability that Eve can predict any of the bits is just 0.5. And so when I talk about this in the future, this equation here is what I might refer to as secure randomness or perfect randomness, because even to our all-powerful quantum adversary Eve, it remains private and unbiased. So this essentially is equivalent to saying that there's an equal chance of 0 or 1, even when conditioned on Eve's extra side information. So the outcomes are still unbiased, even when Eve can model the system, be entangled with it, or have infinite computational power. So we've talked about what is private randomness and why it's important. So now we're going to talk a bit about the different approaches to random number generation and ultimately their limitations and this new approach. So we'll start with classical random number generators, ones that don't rely on quantum effects. The first class of these is pseudo-random number generators. So these are deterministic functions that are based on software. So as they're deterministic, they take some random seed and do some sort of expansion on the seed. So in terms of really maximally secure randomness, because they're deterministic, they're not secure and they're doing expansion. Then the next class we have is physical random number generators. And these are things like coin flipping or thermal noise from diodes. And so in these systems, they're chaotic processes, but as soon as you start to know information about the system, so for example, in coin flipping, as soon as you know a bit about the hand flipping the coin or a bit about the coin, you can start to get some predictive power of the outcomes. So in terms of this maximally secure perfect randomness, this is not secure because it's based on computational assumptions. So this is where quantum comes in. So as I said before, quantum has intrinsic randomness because it's probabilistic. It's not just based on computational assumptions about this model of the system. So as I said, if we can use only quantum effects, we get true randomness. So how do we exploit only quantum effects? Can we build a perfect quantum process? So let's talk about an example of a standard quantum random number generator. So here we have a laser and it's shooting some photons at a 50-50 beam splitter. So half the time they go through the beam splitter and half the time they get reflected. And depending on where the photon ends up, it either indicates a 0 or a 1, and this produces our output. So as I said at the start, it's impossible to build a perfect quantum process because quantum is notoriously noisy. It's called NIST devices for a reason, for example. And so instead we have to model the system. And so if the detectors aren't as efficient as we think they are, or the beam splitter isn't quite 50-50, this all leads to problems because it relies on the model again. So we're having to trust that this model is perfect. And so in terms of security, this isn't secure because we rely on the model being perfect. And so we're trusting the device. So we need a new approach. And the question becomes like, we want to accept that quantum processes are imperfect. So we want to not have to fully characterize the device and be able to use untrusted devices and like just generally put fewer assumptions on the whole setup. And so the question becomes, can we actually get randomness from this approach? And again, I wouldn't be giving this talk if we couldn't, because this is exactly what we're doing with this provable QRNG. So we get, it's called device independent randomness because we no longer rely on the device itself or the model of the device. So in this setup, we can get private unbiased numbers using quantum effects, and we make the device prove how well it's functioning, so we don't have to trust it. It's almost like characterizing it from the outside. So we've gone through what is private randomness and why it's important. We've gone through the different approaches to randomness generation, and so now we're going to talk about this new approach, device independent randomness. So in order to start, we need to talk about the setup. So here we have Alice in her lab, and she's got some random bit generator. But this time, we're going to treat this random bit generator as an untrusted black box. So she's not going to try and characterize it. She's not even going to worry about what's happening inside. It's just an untrusted black box. She's going to give this black box some inputs and receive from it some outputs. Then again, somewhere in the universe, we've got Eve. Eve is this all-powerful quantum adversary with potential side information like entanglement and a full model of the RNG. And they're trying to predict these outputs. And so the task in device-independent randomness is to verify that we have this condition for perfect randomness. We have this condition that the predictive power of Eve for any bit is 0.5. But without actually inspecting the device, we want to do something just by looking at these inputs and outputs. And so for this, we need something called a quantum witness. So we want to be able to witness quantum effects without inspecting or characterizing the device. And so there's, in device independence, there's a few different quantum witnesses you can use, but I'm going to talk about one specific one known as quantum correlations. And so certain correlations between these inputs and outputs are exclusively quantum and can't be replicated in any other way. So this means that if we can show quantum correlations, we can verify that the device is doing something quantum without looking at the internal workings of it. And this, because we're verifying quantum effects, we get this true randomness, and we can limit the predictive power of Eve. So how do we show these quantum correlations? And in order to show this, we play a quantum game. So this game is often called the Bell test, but this is a free party version of the Bell test. So some of you may have heard of this. And in cryptography, it's also referred to as a free prover game. So in this setup, we've got a referee and we've got three parties, Alice, Bob, and Charlie. So the game is, the referee asks Alice, Bob, and Charlie questions 0 or 1, and they answer with either yes or no. And in order to win, Alice, Bob, and Charlie must coordinate their answers in a certain way. And this certain way is that if they're asked 2 questions once, the 3 of them have to answer an even amount of yeses. And if they're asked 0 question ones, they have to answer an even amount of no's. And so this seems really easy, right? Because if you are just having like one referee is having a conversation with 3 people, they all know each other's questions. But the problem becomes that Alice, Bob, and Charlie are not allowed to communicate during the game. So they can't physically coordinate these answers themselves, but they are allowed to chat beforehand. So they can pre-agree a strategy. So this is the first step. So before the game starts, they can all have a chat and pre-agree a strategy. So they've decided on a strategy that Alice and Bob are always going to say yes, regardless of the question they're asked, and Charlie's always going to say no. So let the game begin. So here's our game setup. So each player has their 2 answers, yes or no, and the referee has this set of questions. And there's many sets of questions they'll ask and many sets of answers they'll get back. And so, for example, this first question here is 3 zeros. So that's the equivalent of asking Alice question 0, asking Bob question 0, and asking Charlie question 0. And say the referee wanted to ask questions 1, 1, 1. This would be asking Alice question 1, Bob question 1, and Charlie question 1. And so these are the 8 sets of possible questions the referee might ask. And so to reiterate these winning conditions in a bit of a clearer way, if they're Alice, Bob, and Charlie aren't any of these green question sets, then they have to, between them, answer an even amount of yeses. If they're answered this red question set, they have to answer an even amount of no's. And if they're answered any of these grey ones, they can answer whatever they like. But remember, they pre-agreed a strategy, so they've already got their idea of what they want to answer any question they get given with. So Alice and Bob are always saying yes, Charlie's always saying no. So using this strategy, Alice, Bob, and Charlie are able to win 7 out of 8 games overall. So this means they can win 87.5% of the games. And in fact, this is actually the best you can do with a pre-agreed strategy, because if you think about it, these green and red questions, they have opposite conditions in order to win. So by pre-agreeing a strategy, you can never win both sets at the same time. So the most you can do with this pre-agreed strategy is 7 out of 8. So the question becomes, is it actually possible to do better? And so now we can introduce quantum into this game. So this time, each of them is given a quantum device, and they can, once they get given their question, they're allowed to query their quantum device in whichever way they like. And so incredibly, now we've got quantum, we can win this game 100% of the time. And this is due to a phenomenon known as entanglement. So let's talk about this a bit. So in this game of quantum correlations, a pre-agreed strategy can win a maximum of 87.5% of the games, but quantum can win up to 100% of the games. So by just looking at the combination of questions and answers, if we win more than 87.5% of the games, we're able to witness quantum effects without actually knowing what each of the players were doing, because there's no other explanation for winning more than 87.5% of the games. So to formalize this a little, if we can win this free prover game and get over 87.5% winning probability, it was only possible with this quantum effect known as entanglement. And so this allows us to prove answers are unpredictable to Eve, because quantum gives us this true randomness. So we're able to use this quantified amount of quantum effects. So let's talk about actually using this as a quantum witness. So here's our setup again. We've got Alice in her lab. She's got her random bit generator that's an untrusted black box. So she's not looked at it. She's just giving it inputs and receiving outputs. Eve is trying to predict our outputs, and our task was to prove that we get perfect randomness. And so what's happening now with this quantum witness is this is what's actually going on in this random bit generator. So in principle, this random bit generator is made of 3 separate parts that are being queried with input questions, and it's giving back output answers. And these are being used to try and witness quantum effects like we said about. So by trying to win this game more than 87.5% of the time. And so this is actually analytic. So we can bound this probability here analytically based on how much we win the game. And so I've put a reference up here, and feel free to look at this if you want more details, but essentially I've plotted it in a nice graph because the equations are quite hard to get your head around intuitively. So on this y-axis, we've got the probability Eve can predict any of our bits. And on the x-axis, we've got the winning proportion of games. So this first red line is when we win 87.5% of the game. So this is this best pre-game strategy approach, so the best classical approach. On the other side, the right-hand side, we've got winning 100% of the games, which is the best quantum strategy. So this is when we're using noiseless quantum devices. So when we get 87.5% of the time from our device that we haven't characterized, we don't witness quantum effects. So this means that because we're not using any of this intrinsic quantum randomness, the probability Eve can guess any of our bits are 1. So we don't have any randomness there. However, when we have perfect quantum effects and we get this 100% winning probability, we get this perfect maximally secure randomness. And this is another great thing about using a quantum witness, because in between these two bounds, because we can perfectly quantify the probability Eve can guess our bits, we can use something known as randomness extractors in order to shrink these outputs in such a way that we only extract this intrinsic quantum randomness. I won't get into these randomness extractors now, but they're a whole entire field of their own, but please just trust me that this result's true for now. So we've talked about what is private randomness and why is it important. We've talked about the different approaches to random number generation, and we've talked about device-independent randomness, which is this new approach where you can get provable, private, and unbiased randomness. So now we're going to talk about our protocol and how we implement this. I've just noticed that I've got a question in the question and answer section. Feel free to put them in there, but just so you know, I'm not going to answer these until I finish my talk, and then I'll go through them all at the end. So our protocol for device-independent randomness. So what we're doing at CQC is we're doing device-independent randomness amplification. So this means that we're starting with some bad randomness, so something that's biased or not private, or, for example, one of these standard QRNG approaches, so one that's based on the model and we have to assume trust. Then we use our protocol, and at the output, we're able to get perfect randomness, this provable, private, and unbiased randomness. And so what this does is it relaxes the problem of having to build a perfect random number generator. Instead, we can just build something imperfect and let our protocol take care of the rest. And this is, as I said earlier, this is something only made possible with quantum resources. Randomness amplification isn't possible without quantum. So let's go back to our general device-independent randomness setup. So here again, Alice in her lab, giving her untrusted black box some inputs, getting outputs from it, and bounding this, this probability that Eve can predict her bits to 0.5, this perfect randomness criteria. So what changes? So in this setup, all that changes is that now bad randomness is what's going to be used as inputs in this game. So bad randomness is what poses these questions to create these, to do this game of quantum correlations. So now we've got all the tools, we can actually talk about the protocol itself. So we start with a bad random number generator, and we use this to pose questions to a quantum device. This quantum device is essentially 3 separate parts. So it's playing this bell game, it's playing this free prover game and giving us back answers. So once this has been done many, many times, we get many sets of questions and many sets of answers from the device. We can then put this forward for verification. And this verification step is working out this winning probability. So we've not looked at the internal workings of the device. We've just wanted it to give us outcomes back and use these quantum correlations in the way that we work out this winning condition. So I've put the graph back here just to remind you that when we get a winning probability of greater than 87.5%, we're able to witness quantum effects. So we verify there was quantum effects in the device. So then once we do this, as I said about this randomness extraction, we then use this quantified amount of randomness to get extracted. So it reduces the number of outputs we receive, but it extracts only this intrinsic quantum randomness. So at the final output, we get perfect randomness, this probability that Eve can predict any bit as 0.5. So what have we done? So what's happened is we've started with some untrusted device, and we've asked it some questions, it's given us back some answers, and then we've got provable private randomness at the output. And so the key features of this is that it's secure against an all-powerful quantum adversary. So even now and in the future, with infinite quantum computational power, we still get this provable private randomness at the output. Secondly, we're able to use untrusted quantum devices. So we don't have to characterize the device. We just have to query it with inputs and receive outputs back from it. And this is what is used to characterize it and model it. So we're kind of looking at the device, but without inspecting it. We're looking at it from the outside. And finally, what we're able to achieve is provable private randomness at the output. So we've talked about what is private randomness and why it's important. We've talked about the different approaches to random number generation and their limitations. Then we talked about this new approach, device-independent randomness. Then I've talked about our protocol for device-independent randomness, so this randomness amplification. And now I'm going to talk about how it's actually implemented on a quantum computer. And to talk about this, we need to go back to our scale of trust. So here's our scale of trust. So when we're actually implementing this protocol on a device, we have to think about the device itself a little bit. So on one side, we've got this full trust, which is not good because you're completely relying on the model of the device. And on the other side, again, we've got this no trust, which is the goal. So standard QRNGs, they still sit in this area of full trust. So they really completely rely on the model that's surrounding the device, and they're not good enough in terms of maximal security. So then we've got our device-independent RNG, which really doesn't have any trust. It can be faulty or noisy or even built by an adversary, and we don't have to place trust in the device. So somewhere else, we've got that we trust that the device is not malicious, so it's not purposely built to trick us, but we accept that it may be faulty or noisy or implemented badly, or the model might not hold very well. And this is exactly where our implementation on a quantum computer sits. And so what this means is, what you may ask, what's changed? So why are we not getting this full no trust setup? And this is because the implementation adds a small loophole to the game of quantum correlations. this game here. So you might have heard earlier that I mentioned that these three parties needed to be separated. And so on a quantum computer, we have to assume that Alice, Bob, and Charlie don't communicate during the game to try and win extra rounds. So in full device independence, this is ensured because these three parties, so this one device, is actually kind of made up of three devices because they're spatially separated far enough apart that each of the three players cannot physically communicate in order to help coordinate their answers. So when using a quantum computer, for the measurement step, we have to make this assumption that the qubits don't affect one another maliciously. So now we can actually talk about this full device independent randomness amplification using a quantum computer. So here we have the whole setup, and this time we're going to switch out this quantum device for playing this game with a quantum computer. So instead of questions and answers, now we've got the bad RNG poses circuits to the quantum computer, and the quantum computer gives us back some measurement outcomes. And these are the two inputs and outputs that we're going to put forward to verification to try and certify that this winning probability was greater than 87.5%. And so what we've done is we start with a mostly untrusted device and are still able to obtain provable private randomness at the output, unlike any other QRNG. So here are some actual results. So I said we've implemented it on IBM's machines, AQT's, and Honeywell's. And so again, here's our 87.5% is our maximum winning probability for non-quantum, and 100% is our best case quantum strategy. So this noiseless devices. And so as you can see here, these IBM machines get over 95%, and these ion trap machines like Honeywell's and AQT's, they get 99% and above. So this 99.2% was our best result. And this kind of shows that they're getting really, really close to this 100% maximum best quantum strategy. So it shows that for small 3 qubit machines, they're really starting to get to a point of a nice level of maturity. So this as well is in fact the highest ever winning probability for a pre-prover game in any of the literature. And as I said at the start, implementing this on all these different machines is with help from CQC's ticket compiler, because it takes the same circuit and implements them on these different devices, whilst optimizing on the physical qubits and the actual circuit implementation. So in conclusion, what we've done is we've created a protocol for provable private randomness from untrusted devices, and we've actually implemented the first provable quantum random number generator using quantum computers. In this setup, there's no need to trust the quantum computer's functioning correctly. It self-tests, so it could be implemented badly, and we still get a certificate to say how well it's functioning. We get provable private and unbiased randomness based solely on quantum effects at the output. And this is a really novel approach. So we're able to get security now and in the future, unlike anything else, because as I said, it's secure against an all-powerful quantum adversary. So I'm now going to go through and answer any questions. So feel free to add some more. And yeah, if you would like some more technical details about all of this, then please refer to our paper and archive. But yeah, I'll go through the questions now. So I'll answer from top to bottom. Could you share the slides, at least links to the references? I think this, I guess I'll have to ask Deb about, but I'm sure this is possible. Deb, if you think, can we share the slides?
Yeah, that won't be a problem, Cameron.
Cool, brilliant. Yeah, so I'm sure we can share the slides with everyone signed up to the event. So someone has asked, 0.5 is pure coin flip chance. So in principle, yes, so in theory, if you flip a coin, you do get 0.5 as the chance of the outcome. However, as soon as you start to be able to model anything about the coin flip itself, you can get some predictive power over it. So for example, if I knew exactly the hand that was flipping the coin, I might be able to model the muscles in the hand and get some more chance of guessing the outcomes correctly. So it's based on just computational assumptions. So when I talk about 0.5 is this probability of guessing bits, I'm talking about it in conditioned on Eve, this all-powerful quantum adversary. So someone has asked, what's B and E in the probability of predicting? And so the B always refers to a bit in the output string, and this E is always the quantum all-powerful adversary. So we're saying that this is the probability of someone predicting any of the output bits conditioned on this all-powerful quantum adversary Eve, who may be entangled with the system or have a full model of the device, etc. So someone else has asked, is this useful for blockchain? So I think personally, this is kind of useful in any application where you need maximally secure randomness. So I'm not sure about the intricacies of blockchain, but I imagine it's very useful. So someone's asked a question, can the protocol be improved in the future so that it can be done without any trust in the device? And also, can the problem Google used to show quantum supremacy be tuned into such a no trust protocol? So this is a really good question. So with regard to taking any trust out of the device, this is all down to the hardware now. So there's been implementations of things called loophole-free bail tests. And so in order to take out any trust, you need to implement a loophole-free bail test to produce this protocol. So this can be done, but it's not practical or feasible in the near term. And the second part of the question, so it's kind of different to quantum supremacy because quantum supremacy is talking about quantum computational advantage. So this is that quantum computers can solve certain things quicker than classical computers. Whereas what we're doing in this game of correlations is it's no longer computational. It's saying that there's no underlying assumptions. It's just that quantum is able to do something intrinsically better than classical because this computational assumption, it relies on the fact that the complexities are different. Whereas in this, we don't have such assumption. So someone has asked, what is provable randomness? And is there a measurement that shows that n noisy random quantum generated bits are not based on a given pseudo-random number generator of Kolmogorov-Catrin complexity of order n So I'm not sure about the specifics of the second question, but provable randomness is because in this setup, you get a certificate to say that you get a certificate, an analytical bound on this guessing probability of Eve. So we know that this final output, it is perfect. It's provable in the sense that the predictive power of a quantum adversary guessing any of the bits is always 0.5. And I'm sorry, I don't quite understand the second part of the question, so feel free to write it again. Sorry. So someone has asked, I noticed on the side you were showing noiseless. How are compensating for noise in quantum systems? So this is to do with this game of quantum correlations. And so in this game, we can we get an actual analytical bound on this predictive power of Eve over each bit. And I kind of mentioned briefly and skipped over it about these things called randomness extractors. And so these are the things that we're using to extract this noise. So if you have two independent sources with an analytical bound on the predictive power Eve has over these sources, you can extract just this perfect intrinsic quantum randomness. I hope that answers your question. So QRNG will challenge the hidden variable theory. Is this possible? And so I think if I understand the question correctly, this hidden variable theory is about like local hidden variables. So this is what we're trying to show against by playing this quantum game of correlations, because once you achieve a winning probability of over 87.5%, you can exclude any chance that this outcome was from a local hidden variable. So I think this is in response to the question about quantum supremacy. So they said, I thought Google is working on that. The idea is that if the device returns an answer in a reasonable time, there must be a quantum computer behind it. And so, yeah, so this is of course correct. And it is a test for quantumness, but it also has some underlying computational assumptions, because it's relying on the fact that if this computational problem is hard on a quantum computer, so if someone somehow could find an algorithm that did this in a quicker way on a classical quantum computer, or could parallelize it in such a way, then this would no longer be a way of showing quantum effects. So this is why that's kind of quantum computational supremacy, as opposed to this is just witnessing quantum effects more intrinsically. So someone has asked, can Eve use different forms of noise repeatedly till breaking the system by chance? So I'm not entirely sure what you mean by this question, but of course, like Eve can interact with the system, but the thing is, because we're not trusting the device itself, we're characterizing it from the outside. If Eve interferes with the system, they only ever reduce our probability of winning this game. So they could interact with it badly, but this would essentially mean that it brings this winning probability back down to the local bound. So we can't certify randomness. So if we can certify randomness, we know that Eve has no predictive power on it, but otherwise we can't certify any randomness. So someone has asked, can the inherent noisiness itself be exploited for truly random generation? Maybe personally make a noisy implementation for the same. So this is an interesting question. So the kind of application of this is the fact that we're secure against an all-powerful quantum adversary. So if you wanted to do something noisy, this is introducing classical noise into the system. So these classical chaotic processes. So this is only making the randomness worse. So it never makes it better, because it's adding this computational classical randomness into the mix. So it just reduces your output rate in this sort of setup. So someone has asked, can you elaborate on your quantum extractor? So the specific one we use for this two-source extraction is known as the DODIS extractor. I'm happy to add a link to this when Amalat can send the talk around. But essentially what happens is, because you've got two independent sources that have have known amounts of like probability Eve can predict them, you can use them in such a way using classical algorithms. You can combine them in such a way that makes them a lot shorter, but it kind of combines them in such a way that limits this probability Eve can predict any of the final bits to just 0.5, which is exactly what we need. And these themselves can be quantum proof. So we use quantum proof extractors in this protocol so that our whole protocol is completely secure against all powerful quantum adversary. So someone has asked, I noted you texted this on corporate quantum computers. How did you protect your IP when testing on these devices? So when doing this, we had some certain agreements in place with the companies themselves, and specifically on IBM's machines, using the IBM Q Premium, you can protect your IP and things using these sort of accounts. So someone asked, during the bell game, how many questions will be asked? And so this is something that, so you want to try and eliminate the chance of finite statistics. So what we normally do is use about a sample of about 10 to the 7 different sets of questions, then received answers, because this gives us a really small bound on the chance that, because of finite statistics, this final winning probability could be smaller than it is. And we also account for that in the full protocol by taking the penalty. And if you want to know a bit more about this, you can find out in our paper. Let me go back to slide 104. Someone's just asked, on page 104, if the quantum device is not trusted, how the verification process inside the classical computer can be trusted. So I guess this is to do with this page. So this classical computer, it is really just as simple as calculating how many of the games we won and how many of the games we lost. So this is all done locally in your lab because you don't require quantum effects for this. So this is just something that you personally would be calculating. So it's just calculating the probability that each game was won or each game was lost. So it's kind of something that's easy to verify yourself. So someone has asked, my question simplified is something like, what is the probability that you repeat the experiment twice, you won't get a noisy repetition of your first string? And so in principle, that's the thing, there's a chance you can get a repetition of your first string because, as I said at the start, you can't prove that numbers themselves are random. You can only prove that a process is creating randomness. So what we're doing is we're actually testing and proving that the device is doing something random. So you could, in principle, get the same string again, but you know that your process was creating random numbers. So I think that's it currently for any open questions. Some I haven't answered because they were repeats. Oh, I've just got a new one. So someone has asked, what about a man in the middle attack between the referee and the free provers? I.e., how do we prevent that Eve impersonates the quantum device? And so that's a really good question because if So that's a good question, because if Eve impersonates the quantum device, then we get then this would allow them to get some more predictive power. But this can't happen in principle, because this free prover game is, if Eve was trying to emulate the game, she would, if she didn't want to release any more predictive power, she'd have to come up with a local classical strategy. So she'd only ever be able to give you back information that wins up to 87.5% of the time. So, which we're not doing anything with because we haven't shown quantum effects. And if she impersonated the quantum device and won more than 87.5% of the time, she's actually made a real working quantum device. So this gives us intrinsic randomness. So either way, we're still certifying just quantum effects. So it really doesn't matter in this full device independent setup whether Eve has made the device or not, because we're witnessing quantum effects. Even if Eve has made the device, we can still certify randomness from this. And this is why we can use untrusted devices. So someone has asked, one-time pad, please explain. So let me skip back to the start. So here's our one-time pad. So in this setup, I'll just skip to the full setup. So here's our one-time pad. So in this setup, we've got an adversary, Eve, and another player, Bob, and some player, Alice. And so Alice is trying to send a message securely to Bob. And Bob is somewhere in this public space, but Alice is allowed to prepare her message in a private space. Also, Eve is our all-powerful quantum hacker, and Eve wants to try and find out Alice's message. So in this setup, Alice and Bob had to share a private random key. And so the one-time pad kind of uses this private random key to shuffle Alice's message in such a way that it means that the encrypted message looks random, because you encode the randomness from the private random key Bob and Alice share into the message. So as long as Eve doesn't know this private random key, Eve can't work out any of the message. But as soon as Eve can work out any of the bits of the private random key, she gets access to some bits of the message, and this breaks the security. So someone has asked, but Eve can impersonate a malicious quantum device built to trick us. And yes, of course, but they can not impersonate the malicious quantum device. They can build a quantum device, but as soon as they build a quantum device and we're using it and querying it with these inputs and outputs, this is why we use this bad randomness, because Eve could impersonate a malicious quantum device, but because she doesn't know the complete question set that's being asked, she can never emulate a perfect strategy to give us this winning probability of over 87.5%, because it's happening live in a sense. And so if Eve creates a quantum device that is able to win over 87.5% of the time with these queries from slight randomness, which she can't fully predict, then the device is just producing real, true intrinsic quantum randomness. So it's kind of, the way of viewing it is this bad randomness is used to sample from the quantum device. And because we're using not fully predictable randomness to create these questions, there can never be a strategy, even if Eve created a malicious device that could win more than 87.5% if it wasn't just producing real life quantum effects that provide us with this intrinsic randomness. So someone has asked, could the bad randomness be pseudo or physical? And so the best sort of like bad randomness would be these sort of standard QRNGs, which rely on this model. So they have some quantum effects, but they're not necessarily completely relying on these quantum effects to produce outputs. Because then we have this physical probabilistic randomness. So this is kind of the goal when talking about maximally secure randomness, because the pseudo and physical classical ones, they all rely on just computational assumptions. So when talking about our all-powerful quantum adversary, these don't have randomness to this all-powerful quantum adversary, because they in principle have a model of the device and everything else. So in terms of this fundamental result, we need to use a standard quantum random number generator. So I think that might be all the current questions. If anyone has any more, feel free to email me them after we finish. Yeah, and it was a pleasure to talk to you all and answer your questions. I'll just get back to my end slide because it has my email address on it in case people think of future questions. Yeah, so yeah, there's some more questions that are open, but these are either repeats or just thank yous. So thank you everyone for listening.